Hello and welcome to this video with the title Examples on Analyzing Seismic Events Recorded by the INTAROS OBS Data. My name is Peter Voss. I'm from the Geological Survey of Denmark and Greenland, and this video has been prepared together with Mathilde Sorensen from University of Bergen. In this video we'll show 3 examples on earthquakes recorded by the INTAROS OBS data. OBS is Ocean Bottom Seismometer, and the seismometers has been deployed on the seafloor between Greenland and Svalbard in 2018 and 19 by a group of scientists working in the INTAROS project. We'll show how to do phase picking on earthquakes and locate these earthquakes using the OBS data. Using the Sorensen software for analyzing seismological data. So just to give you an overview, I'll show you a paper presented on this data by Jeddi et al. And this group of authors did a lot of work on these data and also were instrumental in deploying and collecting the instruments. So just to show you where we are, the instruments are deployed here between Greenland on the western side and Svalbard here to the east, and these are the location of the 3 OBS instruments. And this is of course a region with a lot of earthquakes, since it is close to the spreading ridge here north of Jan Mayen and south of the North Pole. But let's get started with analyzing seismic data. First, you of course need some software to analyze the data, and there's a lot of possibilities to analyze software possibilities to analyze it. But in this example, I will use the Sorensen software, and just to give you an overview of Sorensen, this is the Sorensen web page, and here you will be able to download the software. It's free and open. And it compiles on Windows and different Unix, Linux system, and Mac OS as well. It's well documented. There's a tutorial and there's training data sets, so you become an expert. There's a documented manual for the software, and there's a mailing list if you want to get help, and other stuff here as well. But let's just have a look at the manual. It's now a little bit more than 600 pages, but it will tell you that this version that we're using right now is version 12 of the software. So in this example, I will go to my Unix Windows. So I'm here logged into a Linux server, and I have downloaded 3 data set from the IDA server at University of Bergen. So the 3 data set represent 3 earthquakes that we know was occurred in the time the OBS instruments was deployed. So you get the data in data package files in the mini-seed format like this, and just see, if you want to have a look, you can use the IRIS software MSI to see the content of such a data file, and it will show you that there are several different kind of data channels in the files, one for each instrument and one for each data channel. So just to give you an idea of what you're seeing, the HDH is the hydrophone of the OBS instruments. HH1 is one of the horizontals, and 2 is the second horizontal, and Z is the vertical component of the OBS instrument. So you see we have 3 different OBS instruments in this data package. So to get it into the Sorensen software, first of all you need to have a Sorensen database, and you can't process it right away like this, but if you want to make a proper catalog, it's a good idea to make a database. So Sorensen will give you some software, and the first one is called Make RIA, and it will make this database structure. Sorensen uses a flat file database structure, and I called my name PV. I give the starting time of the database and the end time of the database. I just give a good long time window, and it will ask me if I want a RIA database structure or about database structure, or both of them. RIA is for the parametric data, so that's the phase picking and locations, and VAU is for the waveform data. And of course, I want database structures for both, and as I said, it's just flat file structure, so it will now create folders for my parametric and for my waveform data. Since I did it before, it will just tell me that the folders are already there. The next thing I want to do is I want to move my tree data packages into the database. I can do it like it is here, but to make it easier to find for the Sorensen software, it's good to just turn the waveform file name into something that the Sorensen is used to use. So I use the software called Wave Tool, also from Sorensen, and I give the file name, and then I just say I don't want to do anything with it. I just select all the data, and then I turn it into miniseed and like this, and now I get a new file name for that. So, and this is the type of file name that Sorensen wants to read. So I'll just do it for all three files like this. And then for the last one, there you go. So now you see I have three new files. It's exactly the same. You can see that the size is a little bit different because Sorensen is maybe have a better packing for the miniseed file, so it changed a little bit, but not so much. So now the next thing is I want to register these waveform files into my Sorensen database. So I use a program called DF, like this, and I say 20 star something. Oh, I made a typo, like this. Okay, so now I get a file called file list number, and it's just contain a list of the files, and it's giving numbers. So will now use a new program called autorec, and it will ask me if the type of event is a local event. So a local event means that the events are probably within your network or just around your network of instruments, or if it's regional, so you have longer distances, maybe up to 2,000 kilometers from your instruments to the place where the events or earthquakes are, or if they are distant, so it means that you probably have some mantle or core phases from the earthquake recorded on your instruments. But for now we just call these local events. And we want to say yes, let's just let's just copy the waveform files like this, and they will go into the main folder. And again, I'll say this is the PV database, and it asks for the operator ID and also PV, and it will now copy the phases down to the wave folder. So next thing is to analyze these data, and since they are now in my database, so just to give you an idea, so this was the first one here. It now opens what we call an S file, so that's the database file. It's in this folder under the RIA structure here. It's in the PV database. It's in this year and month folder, and this is the file name of the so-called S file. That's where your phase picking are going and the location of the event, and then in there will be a link to the waveform file where you see the raw data. So to open the database, you can either use a Seismic software called Seismic Explorer. It's a very nice graphical user interface with the locator and all statistical tools. And if you have a lot of events, it's a very nice tool to use because you can sort it in different ways. But when you want to just analyze a few events, there's also a command line tool called EEV, and it will you just give the year and month and the name of the database you want to open, and then it will open up asking for the operator ID. You give the operator ID so that if several users are analyzing the data, you can track the history of the event. So now I want to go to day 11 because that was this was in November, so that was day 13 where I had an event here. And this is now the S file that I constructed just before. So it basically just holds a starting time, and that's the same time as the waveform data has. And there's a link to the waveform data and an actual line telling that PV just created this file, and then there's a line. This is the header part of the file, and this is the separator, and below that you will get your phase readings. So just to see, you can give the W and it will tell you where to find the waveform file, and then you can say PUO and it will plot the waveform data. So this is the waveform data from the OBS instruments, and what we see here is just raw unfiltered data. We have the OBS with the name OBEIN for INTAROS, and number 3, number 2 here, and number 1 here, and the different channels. And you will see that we're actually missing the set channel on the on one of the instrument here because there was an instrument failure. Let's have a look when we apply a filter to this one. There's not much to see here. We'll apply some other filters here. Still not much to see. And it seems that we have actually just picked raw data here. There could be maybe a tiny event out here, so we'll just extract that one. We'll set the set and then 2 horizontals here. And we can now ask for the spectra of this event. So we'll type the S key, and if we zoom in, it seems that there is some kind of signal here. Yep. We'll try again. Okay, so if we now assume this is a small earthquake, and if this is the P that we see here, we'll try with different filters. This could be the P, this could also not be the P. Let's have a look. So the question is, of course, what part of it is noise? So I'll zoom out again. Let's see. So in this case, we will assume that we have some P energy out here. So pick a P here, and we assume that this is the S wave coming in here. We can pick the S wave here. So now we have 2 phase readings on this earthquake. There might be a second earthquake after coming in here. It's really hard to tell with one instrument. But we now pick the P and the S wave that we on this instrument. We can ask for the other signals now and zoom in on that same window. Doesn't seem to be any other signals on the other events. At least they are very hard to see on the other OBS instruments. So this was how to pick the P and S wave on this first event in November of 2018. So now I just say Q and I go back to my database. So let's have a look at one of the other events. Since it is in a different month, I go out and then I enter into month 8, and I can also say it was day 11 because that was on the day of the event. I'll just say PV again, and this is now the event file. So I'll do PO again to see the data. I'll apply some filter here, and it seems that there's maybe a little bit more signal on this one. Yeah, so we'll try again. Since this number 3 was missing the set channel, I'll pick the. Normally you would pick the P on the set channel, but in this case I'll just use one of the horizontals. The S wave could be one of these. So I can take the same one, and the same is the case here. I'll pick the P on the Z here and the P on the Z here. This might be the S wave, so I'll pick the S wave here. So now I have enough information to make a location of the event. I'll try some other filters just to verify. You can see the filter up here, so it's the bandpass filter, and now it's from 5 to almost 10 Hertz. I can also use from 1 to 5 Hertz, and there you see you don't get much signal. The signal to noise ratio is really bad. Seems to be a little bit better when you do 5 to 10, and even at 10 to 15 you seems to have some information. Could be that we have an S wave coming in here, so I'll pick it with an S. So I'm picking the P phase and the S phase with the key 2 and 8. If I use the 1 key, I'll get an IP, and 2 I get an EP, and I is the sharp P, and E is if the phase is not, so E is more eminent. So now I have information to do location, so I can just press L and the software will make a location of the event, and the output of the location is what we see here. So of course, first of all, you see there's a headline, the time and the lat long of the event, also the depth of the event, and an important parameter is the RMS of the event. So let's have a look at the different phase readings. So I picked the P on this one, and the location software suggests that this is a PN phase. There's a difference. There's a observed travel time of the P, and there's the calculated travel time, and this is then the residual between the observed and calculated, and that's the same for all of it. There's my S pick here was calculated to be an SN wave, and so on. So these are the residuals between the different picks and then phases from this location, and it seems quite reasonable. It's at least less than 2 seconds, so I'll say yeah, we can accept that. I'll do a U to update this one. If I'm sure, I'll say yes, and I'll go back, and now you'll see that I have the location of the event up here. I can even change the type of the event now. I'll say this is, I'm quite sure this is a local earthquake, so I'll change it to a Q here, so now I get a Q up here. And if we look at the S file now, before we just had a link to the waveform file, we had a header with no information, but now we have location in the information, depth, there's the RMS value here, there's also this gap line telling me the azimuthal gap, and the errors in kilometers on the lat long, and as you can see they are extremely high here because I only have 3 stations, and they're probably not surrounding the event. If you have access to Google Earth, you will be able to see the error bars, and I'll just show you just what it would look like. If I go to this slide, I took a screen dump of my Google Earth, and there you see the location of the 3 instruments and the location of the epicenter path to the instruments, to the OBS instruments, and then this will this represent the error ellipses. So you see this is extremely large. So for sure, to get a better location, it would be good to bring in stations from Jan Mayen here, and maybe also Greenland and Norway or Sweden up here, if you have access to data like this. There's another option, and that is to go into the folder that you're working in, and then you will select a file called gmap.html, and it should at least open up. Oh, you need to type gmap here, sorry, and it will create a location for Google Maps. So if you go back into your browser and then you reload this file, it will automatically send you to Google Maps, and then you can see the location with the satellite image here. And that's very nice. You see we are very close to the spreading ridge here between the 2 plates, and not so far from Jan Mayen. So that's another option instead of using Google Earth. Let's go back and have a look. Sorry, I'll just close this one. So now we picked some phases and we did a location of the earthquake, and we registered some events. Just have a look at the data again and see if we can pick some amplitudes and get an idea of the magnitude of the event. So just take out one of the horizontals like this, and we assume that this is probably, if this is the S wave, normally we'll pick the amplitude in this part of the signal here, and there's some DC offset, so the window will just jump down here. I'll just, for the example here, I'll just pick with my key and press A. I'll pick in with using the Wood-Anderson filter, and that's what you see here. Data are converted to a Wood-Anderson instrument to simulate what Richter would have seen when he gave the Richter scale. So we'll see that the amplitude of this part of the signal is 22.7 nanometers, and there's a period of 2.46 seconds. So now we have amplitude measure on one of the stations. We'll be able to do a location one more time, do L for locate, and now you see that there's also a computation of the magnitude, the ML magnitude here, and it says that this earthquake has a magnitude of 3.4 on this so-called Richter scale using the amplifications here. Of course, for the scale we are using here with the standard seismic software is for Norway, so it would be bedrock, defined for bedrock, and there is some bias since we are on ocean floor lithospheric plates, so this number is probably too low compared to what you will see on other stations located on land, since the waves now are traveling only in the lithospheric plate on the seafloor. So that was just a basic introduction into how to pick phases and pick an amplitude and do a location on an earthquake, and to take data in and do look and have some data to process, and how to open and access the database. And if you want to see more, you can go and have a look in the other videos where you see how to extract data from the catalog, or how to extract these OBS data from different systems. If you do not have data, or if you do not know if there are any events, it's a good idea to visit the EMSC or the IRIS websites to search the area for events. Otherwise, you need to set up a detector or to scan your data to extract the time windows where your events are. But that's all for the presentation and these examples on how to pick some phase readings and try to do a location of these events. And at the end here, I'll just show you that. Go into the last one just to give a quick view of this event that we did on the 17th, and that was the last one. And as you see, I did pick the wrong database, so you'll just do it really fast here. That was on day 21, so this is day 21. I'll just say PO, and wow, there you see there's a big signal here. There's some really interesting things going on with these OBS instruments in this last event, so it's a little bit special. But what you probably see here is now you have the P on these, and this might already be the S wave coming in here. So this is a very big event. So we'll just pick the S here and do location. And now you see I didn't pick so many phases, but I get a really small IMS. Do a location, yes, and there you go. Really interesting stuff going on the seafloor when you do recordings of earthquakes there. Thanks a lot, and good luck processing earthquakes.